Okay, let's go ahead and get started. I want to first of all welcome you to the introduction to acids and bases. This is a unit that I think you're really going to enjoy. You're going to like this one a lot, and let me tell you why. A couple of different reasons. First of all, because of the fact that acids and bases are everywhere. They're all around us. If you're like me, for example, on a hot summer day like today, you like to drink lemonade. And in order to make lemonade, you need lemons. You need lots of lemons. And lemon, as it turns out, comes from a family of fruits called citrus fruits. And citrus fruits contain lots and lots of citric acid. They're paired together with things like oranges and grapefruits and other fruits like that that contain lots of citric acids. If you're like my wife, you make cookies maybe she makes cookies once a month or maybe twice a month. She uses baking soda. And baking soda is necessary for baking, of course, and so as it turns out, baking soda is a base. When you wash your hands, you're washing your hands with a base. So it's not as though acids and bases are some kind of esoteric subject that we'll never talk about or never see or never hear about again. These are things that are all around us. And so we really need to get a firm handle on acid and base chemistry. But I think an even more important reason for the necessity of understanding acids and bases is because of the fact that, folks, we're going to be facing some major issues in our world, and we already are facing those types of issues. And there are things like the process of global warming, for example. So we're going to be looking at questions such as, why is it that the use of or emissions from our automobiles and our factories cause global warming or cause acid rain? Why is it that the acidification of our rivers and streams causes such problems, such big problems for fish and birds and other aquatic wildlife that live in those areas? So all of these are important questions, but in order to answer them, to get a good grip on those types of questions, we're going to need to know some fundamentals about acid-base chemistry. So where do we start? Well, I think a good place to begin is with just a definition. What is an acid and what is a base? Well, as it turns out, our understanding of acids and bases has really evolved over the course of a number of years. And so we're going to take a look at the earliest definition first, and that's the Arrhenius definition. Svante Arrhenius defined acids as anything which contributed to the hydrogen ion concentration of a solution. Anything that contributes to the hydrogen ion concentration of a solution. So for example, if I were to take this container of distilled deionized water, that's what this is. It's distilled deionized water. In other words, it's been purified. All the major contaminants have been removed. And if I were to add a couple of drops of hydrochloric acid from this bottle into the distilled deionized water, maybe 2 or 3 just is enough. 1, 2, 3. What I would find is that the distilled deionized water would have its hydrogen ion concentration increased dramatically by virtue of the fact that hydrochloric acid was placed into the distilled water. The hydrogen ion concentration increased. And by virtue of that alone, hydrochloric acid would be considered, of course, an acid. Now, what's really happening? Let's take a look. Well, what happened in that situation is that when I placed hydrochloric acid into the water, the hydrochloric acid dissociated into hydrogen ions and chlorine ions. This has gas because of the fact that I could have easily have bubbled this hydrochloric acid into the water. But hydrochloric acid is going to dissociate into H+ ions and chloride ions. All right, and we'll learn later that hydrochloric acid is what we call a strong acid. In other words, it dissociates completely. We now know, modern chemistry now helps us to understand that hydrogen ions generally will undergo a process called hydration, where they will couple with water molecules to become H3O+ or hydronium ions. So the real equation that's really happening is hydrochloric acid in association with water is forming hydronium ions and chloride ions. When we see an increase in either hydrogen ions or hydronium ions, and for our purposes they are the same, then we say that the substance is an acid by the Arrhenius definition. Hydrochloric acid is an Arrhenius acid. But what are some other examples? Well, there's hydrobromic acid, there's sulfuric acid, phosphoric acid, acetic acid. All of these fall into that category. And you'll notice something very important about each of these, and that is they all begin with H. HCl, HBr, H2SO4, there's 2 hydrogens in this one, H3PO4, and HC2H3O2. So that gives us a little hint of what's happening. These hydrogens are called the acidic hydrogens. Those are the ones that will leave, that will dissociate to form this Arrhenius acid. So that's it. That's an Arrhenius acid. Now what about an Arrhenius base? Well, an Arrhenius base, in a similar way, is going to dissociate, just like acids dissociate. It's going to dissociate, but it's going to dissociate to add hydroxide ions. So Arrhenius acids add hydrogen ions or hydronium ions, while Arrhenius bases add hydroxide ions. So in this case, if, for example, I had, let's take this container of distilled deionized water, and this time I'm going to add KOH, that's potassium hydroxide. When I add a couple of drops of potassium hydroxide, what I'm doing is increasing the hydroxide ion concentration in a manner that's very similar to what I saw with the hydrochloric acid before. So KOH then is dissociated into K plus ions. We won't worry about the K plus, that's something called a spectator ion, but we will worry about the OH minus, because when OH minus is increased, when OH minus ions increase, we call that an Arrhenius base, an Arrhenius base. So what are some common bases? Well, we've looked at potassium hydroxide, KOH, but there's also sodium hydroxide, calcium hydroxide, that's CaOH2, and aluminum hydroxide, that's AlOH3. Now you may begin to see a pattern here that every time you see the OH, that means a base. OH, OH, OH2, OH3. You got to be careful here because there are some organic acids that end in OH. So be careful for that. Just because it ends in OH doesn't automatically make it a base. All right, but these are some common examples: sodium hydroxide, potassium hydroxide, calcium hydroxide, and aluminum hydroxide. So we're off to a fantastic start. We understand now what acids and bases are from the Arrhenius perspective, but as it turns out, there are other ways to look at acids and bases. And one of the problems with the Arrhenius definition is that there were some compounds, and most notably ammonia. And ammonia was a compound that was known to be a base. But the problem was that ammonia didn't have a hydroxide ion to give away. We knew that it increased the hydroxide ion concentration, but it didn't have the OH to contribute. And so a new theory of acid-base chemistry, or acids and bases, developed. And it was developed by two different scientists, Bronsted and Lowry, both European scientists, at almost exactly the same time. And essentially, the Bronsted-Lowry definition of an Arrhenius acid is the same as for a Bronsted-Lowry acid. In other words, they're both proton donors. We said that an acid under the Arrhenius definition was something that contributed hydrogens, and hydrogens and protons are essentially the same. So for acids, there's really no difference. The difference comes in the Bronsted-Lowry base definition. Before, the Arrhenius definition called a base a hydroxide donor. But we now know that NH3, for example, NH3OH doesn't exist. NH3OH, ammonium hydroxide, does not exist. And so another definition came into being, and that was the Bronsted-Lowry base definition. And according to the Bronsted-Lowry base definition, if an acid is a proton donor, then a base is a proton acceptor. So let's take a look at ammonia here. So this is ammonia right here. Ammonia is being bubbled through liquid water, of course. Ammonia is NH3. And notice what happens. The NH3, I'm going to draw two arrows because this is what's called an equilibrium. We'll talk about that later. But the point is that NH3, you'll notice, becomes NH4+. In other words, ammonia gained a proton. It accepted a proton. So ammonia then is a Bronsted-Lowry base, but not an Arrhenius base because it doesn't have the OH. It is a Bronsted-Lowry base because it accepts a proton, and that's what Bronsted-Lowry bases do, but it's not an Arrhenius base. So we've got now Arrhenius acid, Arrhenius base, Bronsted-Lowry acid, Bronsted-Lowry base. All right, we're off to a great start. Okay, I want to talk a little bit about, while we're on the subject of Bronsted-Lowry theory, because of the fact that Bronsted-Lowry theory gave rise to conjugate acids and bases, I think this is a good place to discuss this. What is a conjugate acid and what is a conjugate base pair? Well, here we see an acid. This is acetic acid, as it turns out. I don't expect you to know that at this point, but this is acetic acid. It's HC2H3O2. It's what we call a weak acid, and it's reacting together with hydroxide. And it's forming an ion called the acetate ion. This is in equilibrium, so I'll put an arrow in each direction. An acetate ion and water. Now, if we look at the left side of this equation, we have acetic acid, and the acetic acid is going to lose a proton. Remember, by the Bronsted-Lowry acid definition, an acid is a proton donor. So notice that this hydrogen was released. This hydrogen went away, and it gave us C2H3O2 minus the acetate ion. So if this is if this gave away a proton, that makes it an acid, and the thing that it becomes is a base. So we call this relationship a conjugate relationship. If this is the acid, this is the conjugate base for that acid. If this is the base, then this is the conjugate acid for that base. Now likewise, if we look at the hydroxide gained or accepted a proton, did it not? Because OH minus becomes H2. So if we look at it from the perspective of the OH minus, since OH minus accepted a proton, it's a base. And the conjugate acid that goes with that base is H2O. Notice that the relationship between an acid and its conjugate base, or vice versa, is a single hydrogen ion. The difference between acetic acid and acetate ion is a single hydrogen ion, and the difference between water and OH minus is a single hydrogen ion. We'll talk a lot more about conjugate acids and conjugate bases later on, but I just wanted to use this opportunity while we were talking about Bronsted-Lowry theory to introduce this conjugate acid and conjugate base pair idea. All right. So we're now familiar with the Arrhenius acid and the Arrhenius base and the Bronsted-Lowry acid and the Bronsted-Lowry base definitions. And what we want to do now is we want to take a look at the last theory that we'll need to know, and that's the Lewis theory. The Lewis theory is electron-based or electron pair-based. And what it holds is that a Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. Remember, that's kind of reversed from the Bronsted-Lowry acid and base definition for hydrogen ions, or for protons rather. So if a Lewis acid is an electron pair acceptor, let's take a look at this acid-base reaction. This is ammonia. It's NH3, and there's a lone pair of electrons on the central nitrogen, a lone pair of electrons on that central nitrogen. This is boron trichloride. Notice I haven't drawn that lone pair because there is no lone pair. Boron is electron deficient. So what's going to happen? What's going to happen is that this base and this acid are going to join together, that the ammonia is going to relinquish its electrons to the boron to allow boron to feel as though it has what's called an octet of electrons. In doing so, it's going to form a bond. And I'll draw that bond in right here. It's between the nitrogen and the boron. By virtue of the fact that the nitrogen atom gives its electrons to boron, a new bond is formed right there. That creates a new bond between the nitrogen and the boron. So, which one is the acid and which one is the base? Well, notice that ammonia, again, gave up a pair of electrons. It gave this pair of electrons up to that boron. So ammonia then is the base, at least by the Lewis theory of acids and bases, and boron trichloride is the acid. All right, we've got our three definitions down now: Arrhenius acid and base, Bronsted-Lowry acid and base, and Lewis acid and base. Okay. Now what I want to do is I want to take a look at the physical and chemical characteristics of acids and bases. The physical and chemical characteristics of acids and bases. And we're going to start with acids. As it turns out, acids as a whole taste sour. We looked at the lemon before. Now, I don't want you to go around tasting different acids. For example, it would be a terrible thing. Don't ever do this. Don't ever go and taste sulfuric acid or battery acid or anything like that. That's awful. Don't do that. But certainly, if you have a weak acid, or even the acid of a lemon, that would taste sour. They're electrolytes. What does that mean? Well, if I had an acid like, for example, H2SO4, if I were to put a little conductivity meter into the H2SO4, a little light bulb would light up indicating that this is a strong conductor, or this is an electrolyte, it's a conductor of electricity. The same is true of even a weak acid, and we'll talk about acids, weak acids and strong acids later, but even a weak acid like acetic acid, if I were to put a conductivity tester into the acetic acid, it would light up a little light bulb. All right, so we now know that acids are electrolytes. What about pH? Well, as it turns out, pH is less, and we're going to talk a lot more about the pH scale for acids and bases in a little while. But before we do that, I do want you to know that the pH of all acids is less than 7. Less than 7. How do we test that? Well, one way we can test it is to look at the reaction to litmus paper. So let's take one of these acids again. Let's take the sulfuric acid. This is a sulfuric acid. And I'm going to be using blue litmus paper. And I want you to notice that blue litmus paper, when it's placed into the sulfuric acid, that it turns red, right? So blue litmus paper turns red when it is placed into an acid. So let's remember that, okay? All right, so that's litmus paper. It also reacts with metals to form hydrogen gas. So for example, if I had a piece of zinc like this, and I were to place it into, this is acetic acid, and I were to place it into acetic acid like this, it would form hydrogen gas. Folks, I'm not going to drop it in there because I prefer not to have hydrogen gas loose in the room. Oops, I just dropped it. Okay, well I guess I will have hydrogen gas loose in the room. I'll put it in the fume hood in just a little while. You may be able to see that hydrogen gas is already beginning to form, okay? At any rate, the point is that, I'm not sure if you can catch that on the camera, but hydrogen gas is forming. All right, so at any rate, so we now know that hydrogen gas is formed when metals are placed into the acid. Now, they are clear when phenolphthalein indicator is introduced. I'm going to take, let's see, this distilled deionized water. Yes, I'll take this distilled deionized water, like that. I'm going to move this just like that. And what I'm going to do is I'm going to place a couple of drops of an indicator. In this case, it's called phenolphthalein. And phenolphthalein is an indicator which tells me whether something is acidic or basic. So if I take phenolphthalein and I drop a couple of drops of phenolphthalein, that's no more than 2 or 3, 1, 2, 3. If I drop a couple of drops of phenolphthalein into the distilled deionized water, and then I put some hydrochloric acid. So let's drop a little hydrochloric acid. What you'll notice is as I drop the hydrochloric acid into the distilled deionized water, is that the distilled deionized water remains clear. That's going to be in contrast to what happens when I place a base into the water in just a few minutes. But I want you to notice that for distilled deionized water, with phenolphthalein in it, when I place acid into the distilled deionized water, it remains clear. It remains absolutely clear. Okay, so that's another relationship that we need to know about acids. So what are some examples of acids? So we've looked at a couple. Hydrochloric acid certainly is an acid. We've looked at hydrobromic acid, HBr, sulfuric acid, H2SO4, nitric acid, HNO3, and a weak acid, what we call a weak acid, and I'll discuss those a lot more as I've said later on, acetic acid. All right, now let's take a look at bases. Bases taste bitter. I'm not going to do it, but if I were to taste baking soda, for example, I would have a bitter taste in my mouth, okay? So bases taste bitter. They feel slippery to the touch. So if I take a little bit of this soap, for example, and I put just a bit of the soap on my finger, I can see that the soap is kind of slippery. It's slippery between my fingers because it's a base. So bases feel slippery to the touch. Just like acids, bases are also electrolytes. The reason is because they dissociate in water. They dissociate in water. The pH of bases is above 7. The pH of bases is above 7. And they turn red litmus paper blue. So let's take a base, for example. Let's take potassium hydroxide. If I were to take potassium hydroxide and get a piece of red litmus paper, just like this, the red litmus paper there we go. The red litmus paper would turn blue. And it does so pretty dramatically because this is a strong base. So it turns very, very blue, and it turns very quickly into that blue color. So remember that a base is going to turn red litmus paper blue. All right? Now, let's take a look at the reaction with phenolphthalein again. Now remember, with water, when I place the phenolphthalein into the water, I'll get a fresh container of phenolphthalein, water. When I place the container of phenolphthalein into the water, or the drops of phenolphthalein into the water, and then place an acid, nothing happens. But let's take a look. I'll put 1, 2, 3 drops of phenolphthalein into the water. Let me stir that around just a little bit, just like that. So I've got my phenolphthalein indicator in the water now. And now I'm going to drop a base. In this case, I'm going to use potassium hydroxide. And let's take a look at what happens. When I drop the potassium hydroxide, this is KOH, I'm going to drop 1, 2, just a couple of drops of phenolphthalein. And what you can see, it may be difficult to see. I'll drop more of that. But you may be able to see that a pink color is ensuing. Okay? I'll put quite a bit as a matter of fact. Here we go. So you can really see that. All right. You shouldn't have to add that much, but I wanted you to be able to see that pink color that happens if the phenolphthalein indicator is in the distilled deionized water. Okay? So that didn't happen with acids, but it happens with bases. So pink when phenolphthalein indicator is introduced if you have a base. So what are some examples then of bases? What are some examples of bases? Well, we've looked at sodium hydroxide. That's an example of a base. Potassium hydroxide is a base. Aluminum hydroxide, a base. Ammonia is a base. And all the organic bases related to ammonia, such as ethylamine and dimethylamine, those are bases. And that's it for this video podcast. So we looked now at the definitions of acids and bases and some of the physical characteristics of acids and bases. And in our next video podcast, we're going to be looking at the pH scale that goes from 1 to 14. So I'll see you on that one. Thanks a lot. Bye-bye.